I hope you're all doing great. I am Mr. S. Thank you for joining me. This question will be the only one for this video. And I thank you again for watching this particular video. We have to solve this differential equation dy over dx minus 2y tan x is equal to tan square x y square. When you're looking at it, you should be thinking about this particular form, which I'm going to put out for you, dy over dx plus py is equal to qy to the power of n. And you'd want to convert this Bernoulli's equation into the linear equation, which would be dy over dx plus py is equal to q. This item will be removed. And this item you can see right over here, which is y square. In that equation right there, it's y square. But when you're looking at it, you can start doing some substitutions right away. Z is equal to y always to the power of 1 minus n, which is y to the 1 minus 2. That 2 from that square is the n value, which is y to the power of minus 1. Then you do the derivative of both of these items. You have dz over dx is equal to, use a power rule over here. You'll have minus y to the minus 2 dy over dx. So this part is done. We have this and we have to convert it into this form, and then we have to do the integrating factor technique, and that's what we will do. So a good logical first step is to take that initial equation and divide everything by y square, because that can eliminate the y square from the right hand side. If I divide all of this by y square, what will I get? I'll have y to the minus 2 dy over dx, and then you know it will apply across. We'll have minus 2y to the power of minus 1 tan x is equal to tan square x, and that helps us out a lot. Now what's the next step? Well, how about you look right over here. You see this coefficient here, minus 1, you'll hit everything here by minus 1. This right here is coming from the derivative of this y component, y to the power of minus 1. That minus 1 right there will apply across, because when you apply it across, it will help you bring these substitutions. You'll have minus y to the minus 2 dy over dx plus 2y to the minus 1 tan x is equal to minus tan square x. Now what's the next step? Well, if you look at everything here, these substitutions will come in, the z substitution and that substitution. Z is equal to that, dz is equal to this. This is dz over dx is equal to all of this, plus 2z tan x is equal to minus tan square x. And here's your linear form. Now you have your linear form, you have to do the integration factor. Integration factor is always e to the exponent integral p dx. What's my p here? It's 2 and tan x. We're looking here at e exponent integral 2 tan x dx. And then when you do this, you're really looking at e with the exponent 2 and then the tan x integral dx. You know that's natural log secant x. And then you know this 2 can come here like a exponent, and that's what you have. When you clean this out using the properties of logarithms, your integration factor is just secant square x, and it will be y is equal to e exponent natural log secant square x. And then natural log y is equal to natural log secant square x, natural log e, which goes away. You bring everything on one side and you combine it under a common log, because you'll have a difference. You'll have natural log y over secant square x is equal to 0. You take natural log on the other side, then you end up getting e exponent 0, which is 1, and then you take secant square x on the other side, y is equal to secant square x, hence that's your integration factor, and the integration factor has been solved. With this integration factor determined, you multiply it across right over here, and then what happens? You'll have secant square x dz over dx plus 2z tan x secant square x is equal to minus tan square x secant square x. You don't need to try to simplify these. You'll just end up making the expression more confusing. Just keep everything as is. There's a certain item, if you do the derivative of this, you'll see exactly arriving at this. And what is that item? Well, you'd have to look at this item right here, and you'd have to look at this item right here, and it would be derivative implicit using the product rule of z secant square x. If you do that, you should end up here, and we can very quickly test it out, because for some reason I'm beginning to doubt myself here, but let's test it out. You have a product rule coming here. You'll do secant square x times the derivative of z, which is dz over dx, plus z times the derivative of secant square x, which you can do with the chain rule, d over du, u square, and then du over dx, secant x, because u here is secant x. You'll have secant square x dz over dx plus z times 2u times secant x tan x. When I bring in the secant x, which is my u substitution, you'll have a secant square x come out of here, and the u will go away. You'll have a 2z secant square x tan x plus that, and we're good. So my initial assumption was good, and it was right. When you're at this stage over here, always just pluck out the item here with the dz over dx, and then look for the z over here, combine them, and that right there is your item which you put over here with the derivative. And then you know here you have a minus tan square x secant square x, which is easy. You have a function and its derivative, it'll be easy. You do the integrals over here. You'll do u substitution here. These will go away, and you'll have a z secant square x is equal to minus. And then now let's do the u substitution. If u is equal to tan x, then du is equal to secant square x dx. And then dx is equal to du over secant square x. This divided by secant square x, or the denominator secant square x, will cancel out with this. What you will end up having is just a u over here with a square and then a du as a result of that u substitution, and everything here is falling very well into place. What you're going to get from here, z secant square x is equal to minus u cube over 3 plus c. But what is u? We know u here is a tan x, so we'll have a minus tan cube x plus c. Z is a what? Z is exactly right here, y to the power of minus 1. But what is y to the power of minus 1? It's a 1 over y. But that's also secant square x over y. If you want, you can stop right here, and this can be your function or the equation for which this differential equation holds true. I say the best answer is exactly what you see over here. Secant square x over y is equal to minus tan cube x over 3 plus c. I don't see any point in taking the secant square x on the other side. It won't very cleanly remove or cancel out with that tan cube x. And I'm confident this answer right here is good, and I will go with that answer. If there is about any editing I will do with this, it would only be this. By means of convention, I would want to write the positive component first. So I would do c minus tan cube x over 3. And now you can see that perhaps this answer might look a little better. Secant square x over y is equal to c minus tan cube x over 3, which is same as this, except you're writing the positive first and then negative later. And that would be a good answer. And that's it for this particular video. This differential equation of the Bernoulli's form has undergone this process of conversion to the linear form, from which the integration factor was determined, and then you did the integrating factor technique and carry it down through, except always in the end don't ever forget to resubstitute the z so you can bring the y back into the picture. And thank you for watching this video. Have a good day. Bye.